So this week we're going to look at data journalism. Next week then it's data in the wild. So this week and next week is actually about confronting you a little bit with reality. So we're here at university. It's kind of the ivory tower often. And you want to know how life looks like in reality. And by now you know data management is great, relational model, blah, blah, blah is great, but then there's reality. And this week is about more use cases that's used by journalists, data journalism. I will tell you a little bit about that and what the technical implications are. And next week I will do the same thing for the entire lecture. So all the material you ever learned about in this class, I will confront it and contrast it with the stuff that people do in reality, and because you should be aware of that. And then once you know that maybe people in reality have a different way of tackling things, then you're prepared. Yeah? Then the shock when you enter industry is not that big. Yeah? When I entered industry after doing my PhD in databases, it was quite a shock. It took a couple of months to understand what the heck are these people doing? Yeah, and I want to prepare you a little bit for that. So today it's data journalism. So what is that about? So now we have only 1 week of data journalism because we did this third part of IMDb last time about Django. And I will give you an introduction on what it is about, a lot of screenshots and links and stuff, and walk you through examples. So here's maybe I'll start with this one. So that's a German news magazine. If you can't read it, doesn't matter. But the main observation here is that this is not just a news article, but there is data being displayed in that news article. And of course, it's not a printout. It's not just a PDF, not even a PDF or real paper. You can add interactive elements here. And when you do if you move your mouse over that data, you get information about these particular points. Yeah? I'm not sure whether you can even zoom in here. No, just the entire web page. Here's another visualization. Yeah, so what you're seeing is plots, visualizations, data visualizations, graphs are now integrated into those articles from journalists. And that has appeared maybe like 10 years ago. Maybe you saw it the first time during the Corona pandemic. Yeah? That was a very popular graph during the pandemic. Yeah, like the positive cases of corona that were recorded in specific countries over time. So here from March 2020 to March 21, patients, deaths, and positively tested cases for corona, and that then again across different countries. So each graph here is a different country. Yeah, so that's interesting information. What's wrong with this graph? Yeah, that's a very important point. So how is it tested in every country? Maybe that countries test differently. So the number of tests you run, the more people you force to be tested, the higher the cases, of course. If you don't force people to be tested, the lower the cases. And that happened here within Germany as well, depending on the current regulations. Yeah, so there's this effect. Yeah? So there you have to be careful. So even within the country, so we are talking about two effects. Even within the country, yeah, be careful when reading those numbers because it's just a minimum. That's just the minimum number of cases you're sure about. Yeah? Those were tested due to some PCR test or something like that. Let's hope it's a PCR test in all of those countries. Yes? A PCR test said, okay, positive case. So that's just the lower bound of what really happens. Yeah? And that changes over time. And so here's a mismatch between what the graph alludes to and what the data actually shows. So the graph alludes to, oh, it's comparable. It's even comparable within the graph. You can compare across a timeline. That's already wrong. First mistake. The second is that you can compare it across countries. Kind of. Really depends on how the data is collected in different countries. Of course, the graph is still informative. It gives you some idea on these lower bounds, but you really have to be careful. And that's the first lesson you should really always have in mind when looking at graphical visualizations of data. Look at how the data was generated. What kind of data was used? How was it generated? Maybe were there possible bugs? What does it really say the data? And don't rush too quickly into interpreting nice visual things. Yeah, here's a third example. I like that a lot. That's election results in Europe. This is an article from the German Zeit magazine. And here you can zoom in. And then whenever you're across a county, like a Landkreis or something like that, you get information about the specific result. Yeah. So this is it's not that much data. I mean, it's just metadata. But it's very interesting because then you can browse to your, maybe you can search for Saarland or something. Saarland, keine Ergebnisse. Let's try something bigger. Doesn't really work. Maybe the search is broken. Yeah, anyway, if the search worked, then you could browse there. Yeah? Okay, so that's data journalism. Here's another example that was called the Paradise Paper. So that happens like every year. Some journalists sit together, and then there is some data leak. Why is there a data leak? Some database gets public. Maybe it's because of SQL injection. Maybe some people didn't attend last week's lecture. Yeah? And then there's SQL injection. Data gets public, happens all the time. I think every week there's a major leak due to SQL injection. And I think here this was also the SQL injection, but there are other prominent leaks that allow you to get access to data. Yeah? And this is about tax evasion of prominent people. And then they collect a lot of data and try to visualize that. We will look into that in a moment. So what is data journalism? So that's the creation of articles with the help of data analysis tools or partially the integration of those tools into the article itself. Yeah? So we have a tool that is like a visualization tool allowing us to highlight certain points or to zoom in and out and stuff, and that's integrated into the article written by the journalist. Well, and if that is about incorporating data analysis into the text, yeah, I mean, we have seen that before, right? If you look at what we did with Jupyter Notebooks. Yeah? So what is the Jupyter Notebooks? That's hypertext plus code. Yeah? So there's these hypertext cells, there are these code cells, and they're intermingled, and you can mix them as you wish. Yeah? And that's kind of the gold standard still these days in many data science and data analysis tasks. And what we're seeing here is that these newspaper articles that were used to be printed out now converge towards something like this, towards a hypertext representation with dynamic elements. The same happens in software development. Yeah? Software development used to be you have an IDE, there's a window for your code, and there's another window for your output. Now that changed. You all of a sudden do software development in this mixed world. And what also happens is in the domain of research papers. Yeah? So the paper meaning it's some piece of research some researchers did, they submitted it somewhere, then reviewers graded the stuff, eventually they said reject or accept. Yeah? If it's accepted, it appears on a conference or journal, and that is then called a research paper. Yeah? The idea is it was printed out. Yeah? And so these papers still appear as PDF documents, and the PDF document has a format, it's typically A4 or letter format, reminiscent of a printout, but it doesn't make sense anymore. Yeah, so there's actually some few journals switching to hypertext where you can submit an HTML with embedded dynamic graphs. Yeah, that's happening, but it's happening way too slow. Yeah, but the idea is the same. So paper research works could also be done in hypertext. Yeah, it doesn't have to be a Jupyter notebook, but it could be an HTML page plus dynamic elements. Yeah. So everything is converging towards hypertext plus dynamic elements. Yeah, so we have to look at how do we model data? How do we query this data? I mean, we looked at that, right? Yeah, so we learned about ER, relational model, relational algebra, SQL, and stuff. But now we look at graphs all of a sudden. Yeah? And the question we will be looking at in the next 15 minutes or so is, okay, now there's a graph. How do we query this data? We look at graphical data models, compare that compare the relational model with a native data model, and then we have to revisit how we query graphical data. You can do that in SQL, but there are specialized languages, one of them being Cypher, and I will give you an idea on how that works. And I mean, why a graph? Because, I mean, in this Panama papers I showed you before, here, that's exactly what happened here. Yeah, so this journalist got a huge data set, I don't know how many terabytes of data, and had to structure the data somehow. And what did they do? They created a huge graph of relationships. Again, like if you see whatever, some crime movie, where the detective has a board, a wall, and then, okay, it has a picture of suspect A and suspect B, and then there's a thread connecting the two. He makes a huge graph, a huge analog graph on that board. And those journalists did the same here. They were distributed all over the planet, so they created a graph, a huge whiteboard, but electronically, in a dedicated graph database. So in these situations, you often end up in creating graphical data. Another example is a social graph, like in a social network. Here's a very simple example. So we have 4 people here, A, B, C, and D, for simplicity, A, B, C, and D. And they are in certain relationships. So A knows C. B meets C or met at some point in time. Whatever, A knows B and so forth. A knows B. So that is how you can model social interactions between those 4 people. And then in Facebook, you have like billions of those nodes, of course. And of course, you could display that in an adjacency matrix as follows. So basically, you have here in the rows, you have from. In the columns, you have to. And here you have an entry for each person appearing in the graph, and here it's the same thing. And then you can represent the graph, of course, like for instance, A0 knows, A knows C. I have these IDs added as subscripts to make it really unique. So I have an ID column, and basically that's this 0, 1, 2, 3. So A knows C. A knows C is that edge, and so forth and so forth. And you can also make make arrows point in both directions, and then you make another entry. So you probably learned that in some data structure and algorithms class. So this looks a little bit like a relation already. However, that's a special case. That's what we call a pivot table. So the difference being that here we also have attributes in the rows. So previously we only had these attributes in the columns, and now they only also appear in the rows all of a sudden. That's called a pivot table. And I show you the relationship here a little bit. So the actual data, what we would call the data in the relational world, as a relation would be something like that. So we have 3 attributes. We have attribute from, we have attribute to, and we have the label, or the kind of social interaction you observed between those 2 persons. A knows B. And now what I'm doing is I make a decision to map to map this attribute to the rows, and to map this attribute to the columns. Of course, if you have more of those attributes in the original relation, you can also put more than one attribute to the rows and more than one attribute to the columns. Actually, it's a decision you can freely decide. And so there are tools allowing you to do that. They're called data analytics tools, OLAP tools. So Tableau, for instance, is an example for such a tool. And there you can basically drag attributes from the relation to columns and rows. And then at the intersection, there's some other attribute being displayed. In this case, it's the label. So A meets D, for instance. So here's another example, a definition of that. So you have at least one attribute displayed in the columns, at least one attribute displayed in the rows from an underlying relation. And at the intersection of each column of, so one of these cells, basically, there's at least one attribute of the underlying tuple of the relation being displayed. That's what we call a pivot table. But the data underneath is relational still, so there's no difference whatsoever. So bottom line, an adjacency matrix can be modeled as a relation. So with that, you can model a graph. Some notes on that. So if the underlying relation hasn't been grouped and aggregated across all attributes in X and Y previously, multiple tuples can potentially appear in one cell. That is why aggregation is usually done beforehand. For instance, in this example, assume, this is an example where you I have Anmerkungen. I think it's here. Yeah, it's there. Boom. Yeah. Assume there's another edge where C not only writes to D, but C also knows. Yeah. C knows D. So that means C writes D. So here I would have writes and knows in the adjacency matrix in one cell. And that would also mean that writes and knows here. Yeah. That's supposed to mean knows. So my handwriting is terrible, I know. That's why I don't do lectures on iPads with handwriting anymore, because it's a lose-lose situation, basically, for everyone. Yeah, right. Yeah, so you might have multiple entries here. Yeah? So that may happen. Yeah? But then in this situation, you could, for instance, you could say, okay, if you have different types, you could also make a type attribute, an additional type attribute here in the relation, and drag it to the rows and the columns to split it up again. Yeah? That's what you could do with these pivot tables. Yeah, so typically you want to aggregate, and the cell displays some sort of aggregate value. Yeah, so if you do a group by from, comma, to, and then you have a select from, comma, to, and then the sum, tralala, the sum of entries or something like that. That's a natural way of dealing with pivot tables. Yeah, so typically that concatenated with that is what you put in the group by in SQL. Yeah? You don't have to, but that's typically what's being done. Okay. Right. Yeah, now if you look at our graph, so we have this example graph. I mean, how could we model that in ER? Yeah, so there are multiple ways of doing that, and that's one example. So you could do something like this. You say, oh, now in this mode, interesting. You could do something like this, where you say, okay, I have a nodes entity type, and I have a relationship type point at, and I make it a recursive relationship type, just adding the label as an attribute. Yeah? Then, of course, I have an N-to-M relationship. I annotate the roles. So this edge represents the from, and so the source, and this to represents the target. And that's how I could model it. Yeah? And then the data would look something like shown underneath. So I have these 4 nodes here, and they have their IDs, and basically the relation that we create from this one, so point at, has here the foreign keys to from and to, yeah, and then the label that we find there. And of course, the label must be part of the key, yeah, similar as with this an actor having multiple roles in the same movie, because of course, as shown above, it may be that there's not only that 0 meets 2, but 0 could also know 2, then yeah, this key wouldn't be enough. Yeah? And that's why it is all underlined here in the model. So that would be one way of modeling that. What would be another way is something like this. You could have a different relationship type for each of the types of social interactions. You could say, yeah, okay, now I have a know, write, and meet. As the relationship types, they're all recursive. As before, then you split that up into separate relations and so forth, but you don't have to attach a label, right? So what's the drawback of that approach? What's an advantage? Any idea? Does anyone see a drawback here? What if you extend your social graph to allow for a new type of social interaction? Yeah? Right, exactly. You would have to extend your data model. You would have to have a new relationship type, add a new relation, as you're saying, true. In the other case, well, no, right? You just add this new label. So this is kind of more flexible. However, so it doesn't restrict as much as this model. Yeah? True. So it's another approach. What you could do is something like this. So for instance, you could say, okay, I have these persons, I give them a label and an ID, of course, and then I have a relationship type communicate with, yeah, and then I could say, okay, there's a medium, yeah, so I try to bring all of these types of communications together. I also have a connection to a point in time. This is dotted, just meaning that actually this is meant to be a link down there. Yeah? So because this point in time should only be modeled once. Yeah, so a person meets some other person at a location at a certain point in time. That's how you could model that. Yeah? And then the location, you give it a GPS. The point in time, of course, has some timestamp attribute, which is at the same time the key. Yeah? You don't need any other attributes. Maybe you add a reason, stuff like that. That's a more involved scheme, which is also easily extensible, because if you invent a new type of communication, yeah, you just set another attribute here and you're done. Yeah? So now we have you saw three types of relational models that allow you to model that social graph. Yeah? So what's the conclusion here? So the relational model is perfectly suited for modeling and storing graphs. We can model graphs in ER or in the relational model in quite different ways. A new separate data model is not necessary for conceptual reasons. Yes, if you conceptually model, so conceptually meaning we're ignoring how the stuff gets implemented, ER is a way, the relational model and the entity relationship modeling is a way to go. So that's fine, check. What about queries? There we have to dig a little deeper. And of course, we will try to do that with SQL. And we need some syntax here. And one is this with syntax, or also called common table expressions. So with is the same as a standard view. However, it's only valid within the context of a query. Yeah? Think about, it's a little bit like an anonymous function in a way. Yeah? So we had this syntax where we said, oh, hey, create a view, and whatever that view returns is just whatever that query actually returns. And recall, when we explained views, we learned that, so when you declare a view, the query inside is not executed at that point in time. It's just an alias. Yeah? It just means now if you refer to this view called foo in a query, basically this text here is one-to-one copied into that statement, and then the query optimizer does all the magic. Yeah? Those are two statements also expressed by these two semicolons. Now we're looking at a local view, and that is something like this. That is with foo s. Yeah, the same thing is in a standard view definition, and then you can use it directly. So there's no semicolon here, and that means this is a single statement. Yeah? So basically, you can also make more definitions in that same with statements. Yeah? So it allows you to structure a single query without having to force everything into a single select statement. Yeah? It allows you to write code that's much easier to read. Yeah? So that's the idea of such a statement here. So that's called with, or common table expression. Yeah, so some details about that. So you can name those columns. Yeah, you can say something like this here. Basically make that, it looks a bit like a function definition, and then you say, okay, this is a view, yeah, that returns a single row, yeah, with values 1 and 42, and the attribute names are n and g. Yeah, and then you can select that, and you get a relation with a single tuple. But you could also do it like this if you want. Yeah? Select 1 as n, select 42 as g, and then you would get the same result. But you don't have to name it, so that you will also see that in practice. So if you write something like that, the database system has no idea about, okay, what are the names of those columns? And then it depends on the database system what it will do. Postgres, for instance, will write something like that, question mark, column question mark. Yeah? So like saying there's no attribute name being defined here. In DuckDB, it looks something like that. It will actually copy the result of that row into the attribute names, whatever. Okay, and now once we have that, we can do recursive statements in SQL. And they're a little bit against what you would expect. So the statement looks like this. So you use the with syntax to define a local view again. And then there's always a non-recursive term and the recursive term. And then there's a union in between. It can also be union all. For the moment, it's a union. Yeah? And then there's again this standard select statement underneath. And the algorithm is something like this. Yeah? So you initialize a temporal set of data with the result of the non-recursive term. So you start by executing whatever is written here. Then you have a second variable, foo, that gets assigned to that, gets assigned that temporary data as well. And then you run a loop, yeah? And the loop will continue as long as there's this temporary set is, contains some data, yeah? So, so as long as the temporary set is not equal the empty set, yeah, then you will call the recursive term on temp as a parameter, and whatever is being returned will be appended to foo. Foo will be your final result. So you keep on looping while this stuff is returning data. While the recursive term is returning data, yeah, you keep on looping, and only if that recursive term doesn't return any data anymore, you break the loop, return what you assembled in foo so far. Let's walk through an example. So let's assume you have this recursive query. So the non-recursive term just returns a single tuple with a single attribute that has the attribute name n and the attribute value 1. Okay? Then the recursive term selects n plus 1 from relation foo. However, only those n that are smaller 3. Again, think about how that is being evaluated. Yeah? So we select all tuples from foo, from the input. Yeah? Those tuples where the n is strictly smaller 3, they pass. And for those tuples, we return whatever n is plus 1. That's what we return. So that's the algorithm again, as from the previous slide. And then you can look at the trace on what happens. So this is how we start with this temp set, okay? So now this recursive term is called with temp, yeah, that is 1. And what does the recursive term return? Well, it returns 2, yeah, the input, that's the input relation, yes, that's the input relation. So the name of this attribute is n, it is strictly smaller 3, so it qualifies, and what will you return n plus 1, and that is 2. Yeah? So this recursive term returns 2 and appends it to foo, to the output we will produce eventually. Now, after this call, foo contains those two tuples, 1 and 2. Now the second iteration starts. You will input here the temp you computed in the previous iteration. Yeah? So that's what we're seeing here. That's what you computed here. That was your output. Now goes into the next iteration. Again, this qualifies because it's strictly smaller 3, your output 3. This 3 is appended to foo, so that is your result. Now you start all over with the recursive term and the temp you computed previously. Well, 3 is not strictly smaller 3, so it doesn't qualify. So no tuple is produced, so the result of this is the empty set. Nothing is appended, or the empty set is appended if you want, but the loop terminates as this condition breaks, yeah? And the return is 1, 2, 3. Okay? Need some time to look about that, to look at that. Yeah? But yeah, let's make it more complex. Yeah, if there's something complex, let's make it more complex. That's what university is about. You can use union all. Union all is, the semantics of union all in SQL is that it won't eliminate duplicates. Yeah? So it will consider everything that is being produced. And you see it in this example. Now I'm changing the query to initially have those 3 tuples, and here say union all. So that means now temp has those 3 tuples. Foo is assigned to temp. You call recursive term with those 3 tuples. Only the first 2 qualify. They're strictly smaller than 3, those ones. Yeah? And they are appended to this temp relation, yeah, like in a sequence. Yeah? Appended to the sequence no matter whether those tuples already exist in the set or not. That's what we're seeing here. So now we have this sequence. We enter the recursive term with a previous result of temp, that's 2 and 3. only 2 qualifies, that will be output as 3. 3 is going to be appended here, okay? So we enter the recursive term with 3, because that's that one. Okay, 3 is not strictly smaller than 3. Nothing is going to be returned. So that is our final foo. The loop terminates, and that is the result. Okay? That's how this works in SQL. Yeah, and let's look at the notebook here. We have a notebook on that. It's also on our web page. Where am I on my machine? That looks good. Graphs in SQL. Close these. Okay. So we're doing that with DuckDB. DuckDB supports with recursive, so sometimes very simple database systems don't support that, but DuckDB does. And we have the same social network graph as we used on the slides. So what we're doing in this cell is basically we are just creating the appropriate schema, one of those schemas I showed you before. And then you can show the data. So here we split it up into different relations in this model. So we have persons, we have knows, meets, and writes relations with the appropriate foreign keys. Again, I mean, you can ignore this leading key here. Actually, the key of such a relation should be the composed key of the foreign keys. Yeah? So the key in the relational model should be start ID and end ID in this example. Yeah? But depends on which tool you're using. Yeah, so then we can do queries like this. Yeah? What do we do? I mean, we have a relationship. Okay, to reconstruct data along a relationship, you have to do a join. And that's what we're doing here. So we can query which persons know another person like this. And that's what we're doing here. So I'm using persons twice here, as P start, as P end, and I have to use the knows relation. So that's a join between 3 relations, persons, knows, persons, along the relationship I modeled. And person is used twice in this example. So as I want to refer to persons 1 and person 2, I rename persons when using them. I say persons as P start, persons as P end. And then I add the join conditions here. So all of this fluff is basically just what are the input relations and how what are the join predicates. Yeah? And then here I can say, okay, this person with that name knows this person with that name. That's all I'm retrieving here. Yeah? Of course, that's a similar result as knows in a way. Yeah? When we go to the knows relationship. Yeah, that is a knows relationship. 0 knows 1, 0 knows 3. So, but what I'm adding here are the names. Yeah? The names are only present in the relation person. So basically, I'm concatenating the names from the person's relation to that relationship type knows here. Yeah, here's another example using recursive queries. Here, basically, I'm computing the sum of numbers from 1 to n. You can also do it with an expression like that. You can, when you play with these statements, you quickly run into the problem that you want to collect sequences of data. That's what we're doing here. In DuckDB, this is called list value and list append. In other database systems, that's called array. So you have an array type that you can use as the return value in your statements. Yeah, and then you can run graph algorithms. Yeah? Here, for instance, the precedence graph. So here's an example. Yeah, so a simple graph. Maybe you hopefully remember when we talked about concurrency control and isolation. Yeah, this waits for graph. That's something like we've seen. So T1 waiting for T2 and T3 and something like that. And then we were reasoning, hey, what if there's a cycle? Yeah, then you have to shoot down the transaction. Remember crazy concurrency control. Yeah? That video we learned about. Yeah? So that's basically what we're doing here. Yeah? So assume you're in a situation, you have a graph, you want to find out whether there is yeah, whether there's a cycle, then you run the graph algorithm. And you can do that in SQL. Yeah, that's fine. Because you learned, hey, we modeled that in the relational model. You can use SQL to query that relational model. And that's what I'm doing here in the naive way. Basically, now I'm trying to find cycles. Yeah? So how do I find cycles? I hop from one node to the other. And in this precedence graph, I only have one type of edge. Yeah, there's not multiple edges like in the social network, meets, nodes, and whatever. Here's just one type. That's this precedence. And now what I'm doing is I'm joining this stuff one by one. Yeah? So whenever I add an edge, I basically have to add a join. Yeah? So the length of the path is determined by the number of joins I'm adding in the SQL statement, which is absolutely horrible. Yeah? So the more edges you want, here's another example. Yeah? So the deeper the graph becomes, or the longer possible edges may become, then you see the more joins you have to add. Yeah? So you end up writing queries like that. Yeah? So now you have a path starting from a node with ID 1, that's the next ID, and so forth, and so forth, and so forth. Yeah? Yeah, so these queries are absolutely horrible. And of course, this doesn't scale at all. That's yeah, terrible to write. But you could do that with recursive SQL as well. Don't worry, I'm not going to go into details in that query. So we wrote a lot of documentation here on what happens. Feel free to check it out back home. But does anybody feel that this is intuitive and readable? Please raise your hand now. No. Yes? Come on. Well, it's not that readable, right? I mean, you look at that and say, what the heck is going on? I mean, a good query language, you look at it and you know, oh yeah, that's the idea, right? Yeah. But here you look at that and basically you first have to reverse engineer what the heck is with recursive doing, what is the trick being played here, what is the guy or the woman trying to do with the statement, yeah? And obviously, no. Yeah, that's not good software engineering, yeah? But it does the same thing, it computes all of these paths through the graph, yeah? So that's a good thing. Yeah? It does a trick. Yeah? But yeah, the interim conclusion is, yeah, SQL, yeah, is quite suitable for very simple queries on graphs. Yeah, you could argue if it's just 2 or 3 joins, maybe it's okay, but still kind of weird. You write it in SQL. For more complex queries, however, only to a limited extent. Yeah, recursive queries in SQL quickly become difficult to read and thus difficult to maintain. And then the question is, what are the alternatives for that? Yeah? So you need a different query language. And one proposal is called Cypher. That was pushed forward in particular by Neo4j. Neo4j is a database system specializing on graph. Did any one of you already use Cypher at any time? No. Okay. Yeah. I mean, the question is, okay, how many use cases do you have for something like that? Yeah? So there are use cases, social networks, data journalism, maybe some others. Yeah, all kinds of network scenarios. So there are specialized databases doing that, and one is Neo4j. Yeah? So it has been developed since 2011. There are a couple of links here you may want to check out. It's open source, but there's also a commercial license. And it's a domain-specific query language, as we're calling this. Yeah? That's a very important term in computer science. Yeah? So generic query language is something like C++. Domain-specific query language, no, C++ is not a query language. No. C++ is a generic language, you would say. Yeah? But SQL is a very domain-specific query language. And SQL is very broad and can be used in all kinds of scenarios. And if you get even more domain-specific, you're at Cypher. Yeah? We're really entering, I'm not saying a niche, but it's a very special case. Yeah? Yeah, and Neo4j also allows you to define a schema. Yeah, so that looks something like this. So the same graph as used before, and the schema is something like that. Yeah, so you can restrict the type of the node. Yeah, you give it a name and stuff like that. Yeah, so it's of type person. It has a name that's of type string and stuff like that. And if you zoom in a little bit, you have edge types like we had in the relational schema. You could also add attributes and stuff like that. Yeah, so that's the kind of schema you can define. However, when you compare it with what schemas in SQL do, you quickly run into that is quite limited. Yeah? So you can constrain nodes and edges, that you can constrain that certain attributes must exist. You have something like keys, but it's far away from a real schema that you can define in SQL. So yeah, there's some ideas there. So I'll just give you some glimpse of how that query language works, and then you play with that also in the assignments this week. But there are many relationships you can draw to SQL. I'm also drawing these on the slides always. Yeah. So here's a basic structure of a query in this Cypher language. Yeah. So you have match and return. So match those nodes and return those attributes. So basically match roughly corresponds to what we use as from in SQL, and return roughly corresponds to what we have in select. Just that they are in the right order. In SQL they're in the wrong order. Yeah? Select comes first and then comes from underneath. Here it's the right order, so the conceptual execution order. So you return all nodes of type person and display the attributes, node ID and name, and that is the result. These brackets here is what's called the ASCII syntax for a node. So here's an example. So basically, the idea here is that expresses a relationship. So that's one node, that's the other node, and that's the relationship that's in between. And you can write that down directly in queries to constrain, for instance, a relationship type. You could say, okay, match everything along a relationship type knows and return that relationship. Yeah, so here, that's what you're returning here. So you say, okay, there's a node A a person A that knows the person C. Yeah? So here only gets relationship types nodes. Yeah? So that's much easier to express this kind of stuff. Here's another example. Right, so here you're leaving away here also here you have these edges. Yeah? You make it directed here. Here it's not directed. Yeah? So here you get it in both directions. Yeah? So you have you get it multiple times actually. The direction of the edge is not taken into account in this example. Yeah? So therefore the matching edge is returned twice, as it matches in both directions, and then you get this result. You also have a with statement similar to SQL that also defines a local view. So here is an example for that returns all cycles up to maximum length 6. Yeah? So what we used in the recursive statement, in this recursive SQL statement, or in the non-recursive SQL statement by adding one join for each hop we're doing in the graph, can only be expressed here just by this number. That's how you would expect it. It should work in a good query language. Yeah? Just specify the maximum length of a path, and there you go. So that's a very readable syntax. I mean, maybe it can be done better, the syntax, but at least in comparison to SQL, it's much better. Just 3 lines of code to get all of these cycles. Right. Yeah, I have a notebook on that, of course. For that, I have to switch to Vagrant, because that depends on Neo4j. Let me do that. Vagrant. So you have it already in your virtual machine installed, this Neo4j. And now if you output. And that's now trying to solve the same things we learned about in the SQL notebook using Neo4j. So we have like a connection to Neo4j similar to a database connection. It works. Now we're creating the schema and creating the data, creating the precedence graph here, and then you can run the queries that I also showed on the slides using this ASCII syntax and so forth and so forth. Yeah? And then here the precedence graph example, you visualize it. That's actually a nice library allowing you to push this stuff around, push the graphs around. Something happening here. Nothing happening here, I don't know why. No output, whatever. Okay, here's a larger example for a precedence graph. And what you then do is, in these kind of situations, the generic algorithm to use is what's called topological sort. So topological sort works like you try to find nodes that don't have an incoming edge, and then you remove those nodes recursively. And that's what we're doing here. Yeah. And if eventually you can't remove nodes anymore, you found the cycle. So that's basically what topological sort is doing. So it's iterating over the graph here in that algorithm. We do it here. You can check that out in detail back home. So now we start with one graph, try to find nodes that don't have an incoming edge. So for instance, T3 would be an example. So it's removing node 3 and then ends up with this graph and so forth, and so forth, and so forth, and so forth, until eventually it finds it has removed the entire graph. And that's the kind of thing you can do with Cypher way more easily than you can do it with a SQL-based database system. Yeah, so the conclusion here really is queries on graphs in SQL versus Cypher. So for queries on graphs, Cypher is lean and elegant language and much better suited than SQL. Unfortunately, that is the result. Yeah? So the winner here is actually Cypher. So overall, in terms of modeling, the relational model is the winner, but in terms of query language, the winner is Cypher. And now the interesting question is now what do you do? I mean, you have data, you have relational data, and you have graphical data. Yeah? So that's something that you see very often in real installations and real data architectures as companies, is that people then eventually install two types of database systems. So they will have a relational database system for everything but the graphs, and they have a graphical database system, say Neo4j or whatever, suitable system for just the Neo4j stuff. And the problem with these systems is, so relational systems are large beasts. They come with a lot of technology. So if we peeped a lot, we looked at that like in terms of query optimization, concurrency control, and stuff like that. Now, if you want to start a separate database system just for graphs, you have to catch up with all of that technology. Yeah? You have to think about, okay, how do I do query optimization on graphs? How do I do my concurrency control? How do I do my transaction manager? Blah, 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 blah. Yeah? So what typically happens is that those systems are very strong on querying graphs in a read-only fashion, but they are pretty bad on everything else, typically. Yeah? So they're not good in concurrency control, not good in all of this stuff, because it's a nightmare to catch up with the relational systems. So what happens over time is that the graphical stuff, just stuff that is needed, is added to an existing relational database system. Yeah? So like these little yellow parts, yeah, like a little extension to the query optimizer, a little extension to indexing, is added to an existing database system. And that happened here, for instance, for PostgreSQL. That's called AGE. Yeah? And that's one way what you're seeing. Yeah? And then what this allows you to do is basically to run a single system, yeah? And not have multiple systems for different types of queries. Yeah, if you think about that, assume you're in a situation like that. Assume your company does it like this. So what could be a possible problem with that? If you, why doesn't this? What could be a problem with such type of solution? Yes, you have two different database systems. Does anyone see a problem with such a setup? Yeah, you start with relational system, then you found out, oh, we also need to manage graphs. Let's install Neo4j or some other graphical system, and now you run two database systems. Yeah?
It's more expensive because you have two different database systems and you need experts for both of these systems as well.
Yeah, the first said it's more expensive because you have more database systems. Yeah, expensive comes with several types of expenses. So in terms of licenses, it may depend on the specific system. It might be that this combined system underneath is actually, maybe it's the same price as that one, or maybe it's this combined price here is less than those two on top, could be. Yeah? But then you said, okay, you need experts to run those systems, to support that. That I would expect is more expensive, yeah, because you need an expert for the graphical system. You need administrator to run that second database system. Maybe you need more hardware if you don't run it in the cloud. That's all true. Yes, that could be more expensive. True. Check. Yeah.
Inconsistencies between both databases.
Yeah, very good. What kind of inconsistencies?
Like you have to store something in both, but you cannot do this in one, and then you only
Yes.
store it in one, and then.
Yeah, excellent. That's an excellent remark. So basically, I mean, this works well if you have completely separate types of queries. Yeah, queries just touching the relational stuff, and other queries just touching the graphical stuff. But what if you have a query that touches both? Yeah, then you have to write a layer on top that breaks up an incoming query and sends one part to the relational database and the other part to the graphical database system. Yeah, that's already one complication. And the other is updates and inserts. Yeah, so now assume you change anything here in your relational database system that, for instance, you add a person or something like that. Yeah? And now you must remember, oh yeah, if I add a person in my relational system, because I also have person records there in my system, I also have to make sure to add it to a graph. So you're entering a transactional scenario where actually your change operations should always be phrased in a transaction against those two systems. Well, you can't handle those transactions within this system alone or within that system alone. You have to have another transactional layer on top all of a sudden. Yeah, that makes sure that you always do both changes in both systems, but not only in one. Yeah, completely stupid, yeah, way of doing it. That's a good point. Yeah, so all kinds of data discrepancies. Yeah, this is a different version than that one. Yeah, outdated data, whatever. Yeah, that may happen. What if this crashes and the other does not crash? All kinds of scenarios. And so that's a very bad idea doing it like that, actually. Yes, so the price of running a separate system for a graph is super high in a real setup, actually. Yeah, so what happens over time, and that's has happened like that for like 40 years or something like that in database history, is the following thing. So 50 years ago, people started with simple initial relational database systems. Yeah? And then people came up and said, I want to have objects, I want to have JSON, I want to have X, Y, Z. Yeah? So there's even here, the graphic goes a little bit more in this direction, actually. Yeah? But at some point, and there was around like 2002 or something like that, there was a big hype about XML. Yeah? XML. And now everybody uses JSON. At the time, people believed in XML for whatever reason. Yeah? So people started developing dedicated database systems with dedicated query optimizers, with dedicated indexes, stuff like that. Yeah? With the argument that if you put XML into this system, it's going to suck. It's going to be so slow, it's not going to work. We have to develop a dedicated XML database system. And this always works for a couple of years. So people develop these kind of systems, and they benchmark the heck out of these old systems. We are 1,000 times faster, blah, 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 blah. And then what always happens is that someone takes an existing system and makes a few tweaks. Yeah? And this example was adding some more rules to the query optimizer and some more indexes to the indexer. And then what happens is it's the other way around. All of a sudden, this system beats the heck out of that one. All of that gets destroyed just by adding some little code here. Actually, was someone from MPI at the time. Some professor in Munich who did that and showed that, yeah, well, what the heck, you can use relational systems, so why are you developing these standalone systems anyway? Yeah, and the advantage is that you get all of these things for free that already exist: concurrency control, recovery, transaction manager, blah, blah, blah. You still have it, yeah, and you're in a single system. That's the way to go. That's really the solution that should be used in practice. But history, of course, repeats itself, not only out in the world, but also in the database world. Yeah, the same happened for graphical database systems. Yeah, as I told you today. Yeah, so there was a time more. I mean, Neo4j started, I don't know, 12 years ago. Yeah, and other systems maybe started even earlier. But now what we're seeing is this stuff is going to be integrated. Yeah? And other major database vendors are more and more integrating graphical stuff, integrating graphical query languages like Cypher into their systems, and then the entire business case for these systems goes away. Yeah, the entire business case these systems have then is maybe the license is much cheaper, and I'm really focusing on graphical stuff, and I don't want to buy the expensive license, but those are business arguments. Those are not technical arguments. The technical argument is always whatever you do, integrate it into an existing relational database system, because that's the way to go. Yeah? And that will happen again. So whatever extension you have in mind, yeah, maybe now it's large language models. Yes, you build a dedicated ChatGPT DB or something like that, yeah? Where you do some cool stuff with querying, using whatever large language model, eventually mapping it to two relations and stuff that already works to a certain degree. Yeah? And then you find out you threw away all of the stuff people developed in the past 40 years. Yeah? It's going to fail, guaranteed, yeah? Because the right solution is take an existing DBMS, integrate your large language models as another layer, whatever, do the additions, there you go. Much better than everything else. Yeah, that's a very, very important takeaway message. If you ask if that's relevant for the exam, I don't know. Conceptually, it's really, you will see that in practice. Yeah? So the way to go is always try to consolidate on a single database system whenever possible. It saves so much money. Yeah, here's a little bit how that works. So this graph extension, how it's called, for PostgreSQL. That's kind of the layered architecture they're using. So basically, they had to bring in Cypher into the system, and they had to extend the query parser to do that. They have to extend the planner and optimizer, of course, and then the executor. Yeah, but that's a great exercise in databases. Yeah? Also, we do that as part of thesis work, for instance, that the student comes, yeah, and then we say, hey, we would like to have this functionality in that system. Could you implement that? And then you have to go through the entire stack, add the functionality, but then the functionality is available. So here's how it goes in SQL. So Cypher is integrated via function calls. Yeah? So here's an example. You can define a function in SQL like this. Yeah, and the function implementation then basically is a Cypher query. Here's maybe another example how it is done in AGE. So basically, you define such a function here. Right, you define the function here, and that's the actual query. And then in the query, you can pass your Cypher statement as a parameter, and then that is exploited by the query optimizer. Yeah? Has some limits, so usually you also have database functions that may return a set, so an entire relation, but that only works for scalar functions. Yeah, that's what I wanted to tell you about Cypher. So in particular, this graph again. Oops. Yeah, the stuff integrate. Always try to integrate stuff into existing systems. That's the way to go. And now with the remainder of today, I would like to show a little bit of data visualization. So as I motivated all of this data journalism stuff today, there are all kinds of fancy visualizations. And with Jupyter, we have all of this stuff at our fingertips, actually, and that's pretty cool. So let's look at some examples of what you can do with this stuff, because I find this really fascinating. So it's an unlimited world. Yeah, this visualization stuff. I mean, there's always yet another visualization you can learn about. So let's look at that. No, I'm still in the virtual machine. Maybe I do it outside. Desktop. Data engineering. So here we go, right? So And of course, we're using data from the database and from the IMDb example. Yeah, and I mean, simple things you may have seen are, it's slow today. Here we go. I mean, you've seen all of these graphs. You can do a bar plot, Excel-style visualizations. On the x-axis, you have the year, and then you have a count on the y-axis, number of movies produced, and hey, was really a sharp increase. And then no one produced movies anymore, right? Right, that happened, right? There was really, I mean, there was a zombie apocalypse at that point, and no one produced movies anymore, right? Or not? Or what's the problem here? I mean, we're 23, right? 2023. So why isn't there? Why did people stop producing movies in 2006? Yeah. What is too old? Maybe it's too simple. I mean, it's kind of. So why did people stop producing movies in 2006? I mean, there were movies that were produced obviously last year. I don't know, Maverick or the new Indiana Jones being produced. But it's not displayed here. Why? What's the problem? Come on. Yeah, the data is not complete. Obviously, the data is stopped all of a sudden. It's super old data, 2005, right? Yeah. So hey, how was the data generated? Yeah, it's an old data set, of course. Yeah, and then what you can do is also what's called a heat map, and that's very similar to what I told you initially today about pivot tables. So how does that look like? Maybe I first show you the result. So that's a pivot table. So what does the pivot table show? Here we have in the rows, we have certain actors, I don't know, some top 10 actors or something like that. And in the columns, we have the genre. The cell displays the number of movies. For instance, Jack Nicholson did with a drama genre, yeah? Or he did with documentary and stuff like that, blah, 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 blah. Yeah? So, and then you have the number being displayed, but also you have a color coding. Yeah? So you have a color palette that defines that if a number is within a certain range, it gets a certain color. So here, the higher the number, the lighter the cell will be displayed. That's a super interesting visualization method. Yeah, it looks pretty cool. Again, what's wrong with this visualization? I think in the elements of data science and AI, I shot that already and asked the same question. Yeah?
I think there are lots of documentaries and dramas in general. And maybe that's why there are lots of people.
Yeah, yeah. So what does it mean?
It's not weighted correctly.
Yeah, from column to column, it's hard to compare because there are more documentaries and whatever, sci-fi, for instance. Yeah, so the relative comparison is very hard. Yeah, just absolutely, you see there are many movies in that space, yeah, but it's very hard to compare. That's across columns. What about across rows? Can you compare one row to the next row? Yeah, didn't see you. Meryl Streep has done less movies than other actors. Yeah, yeah, it's difficult, right? Yeah. I mean, in these kind of situations, you typically try to normalize it somehow, yeah, to make it comparable. We didn't do that, but that's what would be one way to fix. So here's another coloring scheme I'm using, and without normalization again. Yeah, but these visualizations are super useful. Here's another one that's called a word cloud. And the idea of a word cloud is, so here we're just using the titles. There are also IMDb versions of the data set where you can use a description. So, so there's one version of the data set where we have a small paragraph describing the movie. We are just looking at the titles here. And the idea in the word cloud is that you count the occurrences of certain words Yeah, and the more often a word occurs, the bigger it's going to be displayed in the word cloud. So it gives you a nice idea on the topics that are interesting in such a data set. Yeah? So I don't know what the DE means, but life is there, love is very big, adventure, and so forth. Girl, man is much bigger than girl, interesting, die, la, le, maybe la. Those are the French articles we didn't remove, obviously. It sounds like also L is a Spanish article. Here, I think we can kill the stop words. Let's do that. So those are called stop words. Yeah? It's the words that occur very often, like der, die, das in German, or the in English. And then you typically try to exclude those and then get a better picture. Yeah? Here, also we still have les from French, un, lo. Now, yeah, okay, you have to go through all of these languages, but it's getting better. Yeah. So that's the idea. So love, of course, is the biggest thing in life here. And L. Oh, come on. I think we have the time to remove the Spanish. What else do we have? Les. So any other articles? D. Okay, maybe that's die. Maybe probably it's D, right? Der, die, das. Der, die, das should be removed, right? Oh, right. Thanks. What's going to happen here? DE. Didn't I remove L? I didn't remove L, come on. L. Oh, that should fix it. I'm not sure, but uppercase sync doesn't matter. Love, show, man, life, girl. Kid, road. D, world. Yeah, it's getting better, right? Death, life, yeah. Okay, I mean, I think it's pretty cool. That gives you some idea. Okay, other things you might have seen is pie chart, also Excel style visualization. These data visualization things I highly recommend for all kinds of exploratory tasks. Yeah? You get a data set and you want to have a rough idea on what the heck is going on with the data. As you first do visualizations, there's simple statistical analysis, but also these kind of visualizations help a lot. Yeah? The next thing, that's called a violin plot. So basically it's a density plot here. So the density number of occurrences. So all movies that are documentary. Yeah, and then the density plot here just mirrored. And there's a median in the middle. Yeah, that's called a violin plot. Here for the different categories. Stacked bar chart. And that's also a very famous way of visualizing, particularly in research for performance analysis types. Yeah, here you have basically all these actors I displayed before, and then the movies that they did just for these actors, and then per year. Yeah, then you can see, okay, this actor did some more movies in that year than others and stuff like that. Here, for instance, Angelina Jolie did many, many movies, and Johnny Depp as well, and so forth. So. Stacked area chart is another example. Yeah. What's the problem with this one? I mean, it could be argued, yeah. You could say, okay, the data on the x-axis is actually not continuous, it's per year, but the display style is kind of continuous, yeah, but you could argue it's okay. Yeah, it's a boundary case, yeah. But if you have really categorical data on the x-axis, yeah, you don't want to have a line thing or something like that, yeah, because you're connecting data that's not connected. So. You can also make it interactive, and that's this library I'm using here is called Altair. So you will see that when you go through the notebook, it has a slightly different syntax, and the syntax is really much easier than in many other libraries and allows you to do very fancy things. So in particular, it allows you to do arithmetics on graphs. That's what we're doing here. We're combining a heat visualization with a circle visualization, and then we're adding interactivity with a bar visualization. You can do operations on graphs, and that's super cool. And what it means in this specific case, again, we have this pivot plot, but now I can simply click on one of these bars in the example, yeah, and then stuff here in the upper graph gets highlighted. So we have kind of the same visualization happening twice here. That's something maybe you shouldn't do, but just for the purpose of showing the technology. So if we have the number of movies in a specific cell is encoded twice by color and by the area of such a circle. Yeah? Typically, you only want to do one of those. Yeah? You could use one of those for a different aspect of the data. You could use the color to visualize whatever, how long did it take, how much money did you make with that movie or something like that. Yeah? The average money could be one other thing. So you could display two different aggregates at the same time if you wanted. You're using the same. Yeah? Yeah, but then you have this interactive feature, yeah, where you say, okay, you can connect those two graphs. Yeah? And with that, you can actually create kind of what's called a dashboard, yeah? A screen full of graphs where you click on one and then the other reacts, and you can select stuff and have drop downs and stuff, yeah? All in the Jupyter Notebook. Yeah? And that's pretty cool. And yeah, the stuff you have to do for that is, I mean, it's quite impressive when you look at, that's all you have to write to get this magic output here. So Altair is it's a really cool library. We're using that often for our projects. Sometimes you have to look up syntax. It's a bit weird, yeah, but it's really great and much better than other libraries in that space. Yeah, that's just to give you some ideas on what's possible. So it's an unlimited area, and I really like it a lot. Okay, so what's the summary? So what are the data management issues and analysis issues behind the data journalism stuff we looked at? How do we manage graphical data through the relational model? How do we query the data? Yeah, using Cypher or another suitable, readable query language, and preferably fully integrated into relational database system, not as a standalone graphical system. That is the way to go. With that, I'm done for today. Let's call it a day. See you next week.